of course, we're not going to cover however many hours, 16 times at least 0.5 or maybe, so about 12 hours of lecture so far. We're not going to do that in hopefully just about 30 minutes or so. What I wanted to talk about is, so as I said, a sort of summary, and really I want to give it as a knowledge map or knowledge complex. Thinking about what we've done and organizing it in ways where we see the relations and in particular logical independences. So the main thing we've done so far is, and again, in addition to examples, but the main result that underlies our work is the fundamental theorem of characteristic classes, I'll call it. So there are classes in the base of a vector bundle. So this is associated to a vector bundle V, E to B. We have these characteristic classes which are natural. Which satisfy the Whitney-Sum formula. There's some other axioms, but I'm not going to worry too much about those. I'm just going to mainly list naturality, Whitney-Sum, and of course, and for which the first Stiefel-Whitney class of the tautological line bundle over a projective space is non-zero. And then the other thing is that these constitute all mod 2 cohomology characteristic classes of unoriented real vector bundles. Of course, those are the vector bundles we've been studying so far. So that's the fundamental theorem. And what I wanted to do is kind of map out how we get there. And again, we apply this to, for example, get some non-immersion results for projective spaces. That's been our main application. We'll also come out to group cohomology in about a week or so. I'm also going to do some cobordism. So we'll come back to more applications. For a few of those, I'm waiting for us to go ahead and do the churn theory, where some of the calculations are more fun because they're over the integers. So the question is, how do we get here? How do we set things up? And let's just go to the very beginning. We've got, of course, first thing is just what are vector bundles? We talked about that. What's the basic definition? What are some basic properties? It's a category of limited use, but still as a category, but the keys are these pullback morphisms, and all these additional structure on the category are these endofunctors, like direct sum. Again, those are critical in things like algebraic and differential geometry. Then we, one of the first things that we'll need to talk about, or we did talk about, and you need to talk about, are Grasmanians. and tautological bundles. And I'll sort of color in some, since we're talking about bundles. Of course, vector bundles, as you might imagine, there are arrows everywhere. I'm going to ignore arrows that are compositions and just talk about sort of where things are more directly needed. But the other thing is our approach to characteristic classes has been through, and I'll call this topic 0 because I think of this as something you develop before, are these tome cochains. And again, so that's, folks who've been watching this will know well, to a map between a manifold, this is the mod 2 theory, is all we need for mod 2 characteristic classes. To a map between manifolds, which is smooth, we get a cohomology class if W has no boundary. We get a cohomology class in the cohomology of the manifold mapping 2, and that cohomology class is in degree the codimension. So this is sort of not a standard topic, but I find them very useful and compelling, and we actually use them for our definitions of characteristic classes. So that's what comes next. I'm going to sort of delineate things a bit by so these will not only have logical implications, but some sort of groupings. I think of these as sort of background. They all feed into the definition. I'm going to do it this way. Define Wn minus I to be the tome class of the, or is represented by the tome class of this smooth object that I call dep I plus 1 of our bundle E. So E is of rank n, and dep sits over a direct sum of I plus 1 copies of E, which of course is homotopy equivalent to B, and so the tome class of that map can then be pulled back to B to give some cohomology class. So, and clearly, this definition uses everything above, including the Grasmanian, because this dep is defined in terms of linear dependence. Well, that's what, oh, sorry, this is dep hat. This dep hat is a sort of a resolution which uses a Grasmanian-like construction to talk about linear dependence through the subspace that you're spanning when you're not dependent, when you're not independent, sorry, when you are dependent. So you need Grasmanians to define this dep hat. It's manifestly a tome cochain definition. So all that background goes into this definition. So that's all well and good, but you want to develop the main properties. But then in this perspective, I would say that a main The next step is a calculation. Actually, let me move this. Is the calculation of what these classes are for a direct sum of line bundles. So I'm going to list that as 4. This key early calculation. This is a calculation that we did using the Whitney sum formula, but then as I proved last time, if you could do it another way, and I outlined how, then you can prove the Whitney sum formula. So a key example is the external direct sum, which you can just think of as Cartesian product of tautological line bundles. So yeah, and then you show that Wi of this is so if this is our E, and the bases are product of RP Ds, then WIE is sigma I, the isometric polynomial in the cohomology of a product of RP Ds. And here, let's say D is bigger than the number of these, which is say N. I'll just assume D is bigger than N for usefulness, for ease. So for that key example, actually, all you really need is the definition, of course, and as we'll see, some more about Grasmanians, and maybe we can even say some better understanding of cochains. So the main thing you need are these: is the definition, but we also this calculation, as I'll say a bit at the end, uses a bit more Grasmanians, and it also it sort of elaborates how you use cochains with chains to do a calculation through pairing, at least in the way I like to think about it. So you can make that key example, and that will be crucial. But at the moment, you could just think of it as an example. Then you get back to sort of the big picture. You've got the classification theorem. Which says that vectin over X is homotopy classes of maps from X to GRN R infinity when X is paracompact. Otherwise, by vectin just means something like tame bundles. You don't really need anything there other than vector bundles and Grasmanians. So I'll not make the picture too complicated. I'll just draw the implication from Grasmanians and sort of have the implied implication from vector bundles. And then the third, so this was some work, and a third piece of work are the Schubert cell structure. And in fact, this is also all it really depends on. Here, definitely you don't need sort of general vector bundles. You just need to know about Grasmanians, right? So that's something you could do directly after you do 2. So notice if you want to present things in logical order, you still have plenty of leeway. You could go right from 2 to 6 if you were designing topics in a book or lecture series. And that's only if you want. You could always sometimes prove something assuming previous results that you need and then come back to prove those. Nothing wrong there. That's Milner and Stasheff do a lot of that. From there, we get the main results because we can prove the Whitney sum formula. Starting to run out of room, but the proof that we used definitely just use this all 3 of the things above. Well, actually, just the no, we didn't need Schubert cells. We just need the classification theorem, which allows us to just consider the which allows us to just consider the universal bundle in order to prove a direct sum of universal bundles in order to prove this. And then this key example, actually, because, actually, sorry, and we do need Schubert cell structure indirectly because, now that I think about it, we use injectivity of the map from the Grasmanian to a product of projective spaces. So this is the classifying map for gamma 1 cross gamma 1 on cohomology, is going to send those to the symmetric polynomials. Inside the cohomology of Grasmanians, and the fact is that this is injection uses the Schubert cell structure as well as what we know of this key calculation. And then the Whitney sum formula uses that injectivity. So maybe I should have I'll call this 7 and the other one 8. So that's sort of how I prefer to put the fundamental theorem together. No Steenrod operations needed, no Leray-Hirsch. You have this key example. You have a lot of other things that are standardly done, the classification theorem, Schubert cell structure. You deduce this injectivity is because, well, Schubert cell structure gives you an upper bound for cohomology. The key example gives you a lower bound in the sense that the cohomology of the Grasmanian contains this symmetric polynomials as a homomorphic image, or has these symmetric polynomials as a homomorphic image. But then you look at the ranks by Schubert cells and you see that there could be no kernel. So the Schubert cell structure is key to give you injectivity of this map. Once you have injectivity of this map, the Whitney sum formula, as I showed last time, follows from the putting 4, 5, and 7 together. The classification theorem tells you you can think of that universal example. The injectivity then says that you can identify what happens for that product, and the Whitney sum formula comes out. So again, maybe this is indirect, but it is, the key example is key for getting that injectivity, and that injectivity of the map from Grasmanian to the product of projective spaces is one of the sort of biggest results in the end. Again, as I said, it's a weak splitting principle, let's call it. So let me say another word about, so that's all that I want to say for that. That's what we've done so far. Again, applications so far include non-immersion results, and we'll have a few more as we go along. It's taken a few weeks, which makes sense if you hadn't really thought too much about vector bundles before, to go ahead and get those questions in front of you and then start answering them. It takes a while. So, so let me say a word on the proof of 4, the key example. So RE4. Because again, I feel like I didn't say it as I wanted to, as well as I wanted to, but the way you think about this, I think about this characteristic class of a direct sum of line bundles in this framework, using the tone cochains as follows. So I want to calculate Wi of to calculate this Stiefel-Whitney class, you use standard sections coming from, so this sits inside R, so product of RPD cross. Each line in RPD is an RD plus 1, and really then we have well, I could do it either way, but this exhibits the line bundle as sitting inside a trivial bundle. And so we can use those to make sections. And I won't say how, but the point is that the definition of, so if we use coordinate projections to define sections, as we did at the end of last lecture, and I just chose not to try to redo all of that this time, then the vanishing you end up looking at the preimage under this direct sum of sections of this dep hat. So and you do some analysis and you realize that that you're looking at this subspace of the Grasmanian of I-planes in R I plus 1 cross this product of RPD of, what I want to say is that the lines have rank, which is, the lines have rank one less than you'd expect when they project them. So this is a subspace of V and L1 through Ln, so that each Li is in the preimage of V when I project onto Ri plus 1. So this is a more precise way of saying I'm looking at a in lines in dimension D, which when I project into dimension I plus 1, they span something of dimension I or less. And the point is, so n is greater than I. The point is that the first I minus 1 are sort of free to be generic, and then starting at the ith one all the way through the nth one, there's a codimension 1 condition for each of those. So so you can check that the dimension of xn minus I is what? It's, well, GRI, RI plus 1, that's just a RPI, so I get I for that. And then I project onto those lines, and then I've got, but they can, each of those lines sits in an R D minus 1, because V is codimension 1. That means its preimage is codimension 1. So each of those lines is sits in a codimension 1 space. So I have in lines, each of which really I'm sitting in an RP D minus 1 in the fiber. Okay, so in other words, what this is doing is I'm using the fact that xn minus I sits over the Grasmanian with fiber a product of R P D minus 1. From that, the dimension result that I just said is immediate. Yeah, well, so xn minus I, I could project down to the Grasmanian, or I can project down to product of RP Ds. And the point is that this has codimension n minus I. So in fact, the sketch is that sketch of what happens is that you're looking at the definition of W n minus I, which is, dependence of I plus 1 sections. If you choose your sections using projections in the trivial bundle that gamma is defined in, then you're led to this x n minus I, and you're taking the tome class of the it with its projection over RPD. And then it's another calculation that's equal to the n minus ith symmetric polynomial. So this is the summary of 4, which is not something that I just outlined for in the case, I think it was n equals 4. This gives it a little bit more sort of general notation, and sort of a cleaner. This is the flow of things. We first analyze W n minus I through sections, as we do by definition, and then we're led to this subspace. Well, it's not quite a subspace. Something that sits over Xn minus I sits over an RPD, and it's codimension n minus I, and it is what we would get by sort of pulling back the depth construction over the Grasmanian. And then what we realize further after, say, testing it on homology basis is that we have a symmetric polynomial. All right, so that's what I wanted to say. So mainly, we go back, here's our knowledge map, our knowledge complex, vector bundles, tone cochains, Grasmanians, characteristic classes, key examples, classification theorem, and finally we get the Whitney sum formula and the cohomology of the Grasmanian. Knowing that will also then tell us that these Stiefel-Whitney classes, there are no further characteristic classes.